Black holes are not a thing. Black holes are not dead stars. Not all stars can become black hole, and black holes are not black. As Stephen Hawking would say, they do radiate and they are not eternal. Today we are going to understand black holes from the very depths of. We are going to understand the facts behind these myths. We will be starting all the way from Einstein's relativity. While this one video will obviously not be enough to cover everything which we know about black hole, especially the spinning black hole, what we are going to do is that start with the very base of it, and I'm going to give you the base to think on about black holes. It all started during World War I when Karl Schwarzschild found this remarkable solution for Einstein's equation. He did not call it black hole. In fact, it won't be called black hole till many decades later. He says, imagine this thought experiment that we crush an entire star to a point. Don't ask how we do it because that's just nonsense, but let's imagine it for the sake of this thought experiment. He wanted to understand what happens to the space-time near that pointy, massive star. Now, we all know that death of massive and huge stars leaves behind a black hole. But black holes are more fundamental than that. Black holes are not just dead stars. So to understand that distinction, that difference between those, let's dig a little bit deeper. Let's go to Einstein equations. They say that matter and energy tells space-time how to curve, and curved space-time tells matter how to move, as John Wheeler famously quoted. When Schwarzschild applied his thought experiment in Einstein's equation, and he finds a remarkable solution, there was something weird in it. He found this region beyond which not even light can escape the gravitational pull of that star. So what does that mean? Think about it. If light cannot escape the gravitational pull of the star beyond this region, inside that region, that means no matter can, because nothing can travel faster than the speed of light. And if no matter, no light, no information can leave that region of space-time, anything happening inside that region is basically tugged away, kind of invisible to an observer outside that region. It feels like a horizon, that anything happening inside this horizon cannot reach us. A horizon for events. And hence we call it event horizon. That event horizon is the black hole. The black hole is not at the center of it. The black hole is not the center of that pointy star which we crushed. The black hole is not inside this event horizon. That surface in space-time, that is defined as black hole. But if you go there is nothing really at the event horizon. It is basically an empty region in space-time. So think about it. This event horizon, and hence this black hole, is not a thing. It is a region. It is a region in space-time which is basically cut off from this outer universe. It's just this death of a massive and giant star with ever-increasing density creates this event horizon. People think that both of them are same. That black hole is some sort of dense matter. But it is not true. For all we care, that event horizon is the black hole. And we don't know what happens inside this event horizon, because remember, no event can cross that horizon and we can't get any information out of that region. But there is another weird thing about this event horizon. It only works in one way, in one direction. So anything happens inside doesn't go outside. Any information from inside does not go outside. But anything, any matter, energy, light, or whatever can go inside that event horizon. So any event outside can influence something inside, but any event from the inside cannot influence something outside. Wait, but what happened at the center? In order to understand that, let's create a black hole from the death of a giant star. So imagine a huge star, approx 20 to 30 times mass of our sun. How does a star produces energy? Well, you will say nuclear fusion, right? So hydrogen atoms get fused and create helium atom. But how does that exactly work? So if you collect a lot of hydrogen atom, let's say, because hydrogen atom is the simplest form of atom there can be, right? There is just one proton and one electron. So if you collect enough of them, obviously they have mass, so they are going to feel the weight. So they start collapsing under their own weight. That collapse raises the temperature of the star, and that raise in temperature will keep increasing until it starts fusing hydrogen atoms into helium, or I should not say atom, hydrogen nuclei into helium nuclei. That generates energy. It generates more energy than what it took to fuse two hydrogen nuclei. And how that energy exit this star? It exits in form of radiation, and that radiation exerts a pressure all the way in outside all direction. So we call it radiation pressure. So that radiation pressure basically holds the star from further collapsing on its weight. And that's how we have a definite kind of size for our sun, let's say. Now think about it. That hydrogen fuel, or those hydrogen nuclei, will eventually run out. What happens when they run out? Well, the radiation stops because the fusion stopped. Thus the radiation pressure is no longer there, and the star starts collapsing again, and the temperature starts rising again. That temperature will rise and become enough to fuse two helium nuclei into something heavier like carbon or a little bit of oxygen nuclei. This phenomena keep going. Then let's say the helium will run out, and then the carbon, whatever, they will fuse. This thing keep going till iron, but it stops at iron. Why does it stops at iron? Simply because when you do the math, you will find out that the energy requires to fuse two iron nuclei is basically more than what it generates. So that's not energetically balanced or energetically sustainable reaction. When it stops at iron, suddenly the fusion stops again, the same thing, the radiation stops, and hence the radiation pressure stops, and the star collapses on itself. That collapse is extremely fast and sudden, and that creates a shock wave, which we actually know as supernova. That shock wave raises the temperature way higher, and that's how we get all the nuclei heavier than iron. And then that supernova burst and spread all those heavier nuclei in the universe, and that's how you and I are made up. We are not just made up of hydrogen, and supernovas are the region. What's left there can sometimes become neutron star based on the mass we started with. Neutron star are another really cool objects. They are basically a giant neutron because the electrons are pushed way in the nucleus and collapse with protons, and we have just super dense object left. But that's a discussion for another video. However, if we have enough mass, the star will keep collapsing on itself, and it will eventually cross that region which we just talked about, the event horizon. It will cross it, and then nobody knows what happened, because remember, we cannot know anything beyond this region, which we call event horizon. And this is how you make a black hole out of a giant star. What happened at the center? Well, if you keep probing a smaller and smaller distance, if you keep going towards this center, remember that quantum mechanics needs to be there. Quantum mechanics is in play when you are probing very small region of space-time. And we tried to put quantum mechanics in theory of relativity, and turns out they are not compatible. And this is where the current frontier of physics is working. That remarkable solution by Karl Schwarzschild basically tells us what is the limit of this theory of relativity. At the singularity, we don't know what happens. Our current understanding of space-time breaks down. And as Roger Penrose said, we don't even know what happens at the singularity. What is there? As quantum mechanics is in play, there might not even be a singularity. Nobody knows. Black holes are coolest object in the universe. Not metaphorically, but literally. They have almost absolute zero temperature, but not quite. They do have very small temperature, and they do radiate. The radiation is known as Hawking radiation, and the temperature is known as Hawking temperature. And if black holes radiate, technically they are not black. I'm creating a playlist on black holes starting with this video, and we are going to cover so much which right now I know about black holes, and so much which right now I do not know and understand, and will be learning. And speaking of learning, I learned a great deal about black holes from Janna Levin. She's a cosmologist and a professor of physics and author of many books about black holes, such as Black Holes Blues and Black Hole Survivor Guide. Needless to say, I'm a big fan of her, and this video was inspired by her work. But if we go a step backward, we need to understand first what gravity is. You must have heard that gravity causes curvatures in space-time. Not quite. Gravity is just another name for the curvature in space-time. If you're still watching and reached here, I know that you're gonna absolutely love this deep dive we did on gravity in this video here.